Hello students, and welcome to the lecture on combinational logic circuits. After this lecture, we will be able to learn the following objectives. Explain standard combinational circuit blocks. Define sequential logic circuits. Discuss finite state machines. Understand the concept of registers. Explain standard sequential logic circuits. Let's start with the introduction of combinational logic circuits. Combinational logic circuits are electronic circuits that produce outputs based on the states of the inputs. Unlike in sequential logic circuits, the previous outputs do not partly determine the next outputs. The transistor-transistor logic, or TTL family of circuits, also implements combinational logic circuits. Voltage levels are either 0 volts direct current, VDC, or low voltage level, M+5 VDC, or high voltage level. A buffer is a TTL circuit that outputs a level that is the same as its input, while an inverter outputs a level that is the opposite of its input. Combinational logic circuits, like the buffer and the inverter, are single input circuits. There are also two input logic circuits known as logic gates. A common logic gate is the OR gate, which may have two or more inputs. Given the first input is input 1 and the second input is input 2, a two-input OR gate will output a high if input 1 or input 2 is high. A two-input AND gate will output a high if input 1 and input 2 are high. The combinations of input levels determine the output. Let us now discuss the standard combinational circuit blocks. Unlike sequential logic circuits whose outputs are dependent on both their present inputs and their previous output state, giving them some form of memory, the outputs of combinational logic circuits are only determined by the logical function of their current input state, logic 0 or logic 1 at any given instant in time. The result is that combinational logic circuits have no feedback, and any changes to the signals being applied to their inputs will immediately have an effect at the output. In other words, a combinational logic circuit, the output is dependent at all times on the combination of its inputs. So if one of its inputs condition changes state from 0 to 1 or 1 to 0, so too will the resulting output, as by default combinational logic circuits have no memory, timing, or feedback loops within their design. The three main ways of specifying the function of a combinational logic circuit are Boolean algebra. This forms the algebraic expression showing the operation of the logic circuit for each input variable, either true or false, that results in a logic 1 output. Truth table. A truth table defines the function of a logic gate by providing a concise list that shows all the output states in tabular form for each possible combination of input variable that the gate could encounter. Logic diagram. This is a graphical representation of a logic circuit that shows the wiring and connections of each individual logic gate, represented by a specific graphical symbol, which implements the logic circuit. Encoder. Encoder is a combinational circuit which is designed to perform the inverse operation of the decoder. An encoder has n number of input lines and m number of output lines. An encoder produces an m-bit binary code corresponding to the digital input number. The encoder accepts an n-input digital word and converts it into an m-bit, another digital word. Priority encoder. This is a special type of encoder. Priority is given to the input lines. If two or more input lines are 1 at the same time, then the input line with highest priority will be considered. There are 4 inputs, D0, D1, D2, D3, and 2 outputs, Y0 and Y1. Decoder. A decoder is a combinational circuit. It has an input and to a maximum m 2n outputs. Decoder is identical to a demultiplexer without any data input. It performs operations which are exactly opposite to those of an encoder. Examples of decoders are code converters, BCD to 7-segment decoders, Nixie tube decoders, relay actuator, multiplexer. Multiplexers also are used in building digital semiconductors, such as central processing units or CPUs and graphics controllers. In these applications, the number of inputs is generally a multiple of 2. The number of outputs is either 1 or a relatively small multiple of 2. And the number of control signals is related to the combined number of inputs and outputs. Types of multiplexers also are used in combinating communications. A telephone network is an example of a very large virtual multiplexer that is built from many smaller discrete ones. Demultiplexer. A demultiplexer, or demux, is a piece of equipment that takes a single signal carrying multiple payloads and splits it up into several streams. They are often used in telecommunications to carry signals over long distances. A demultiplexer is the opposite of a multiplexer. A multiplexer, or mux, takes signals from many sources and puts them into a single signal. That signal is transmitted wherever it needs to go, and then disassembled at the other end by a demultiplexer. Adders. In computers and other kinds of processors, adders are used not only in the arithmetic logic unit, or ALU, but also in other parts of the processor, where they are used to calculate addresses, table indices, and similar operations. Half adder. Half adder is a combinational logic circuit with 2 inputs and 2 outputs. The half adder circuit is designed to add 2 single-bit binary numbers, A and B. It is the basic building block for addition of 2 single-bit numbers. This circuit has 2 outputs, carry and sum. Full adder. Full adder is developed to overcome the drawback of a half adder circuit. It can add 2 one-bit numbers, A and B, and carry C. The full adder is a 3-input and 2-output combinational circuit. N-bit parallel adder. The full adder is capable of adding only 2 single-digit binary numbers along with a carry input. But in practical, one needs to add binary numbers which are much longer than just 1 bit. To add 2 n-bit binary numbers, one needs to use the n-bit parallel adder. It uses a number of full adders in cascade. 4-bit parallel adder. In the block diagram, A0 and B0 represent the LSB of the 4-bit words A and B. Hence, full adder 0 is the lowest stage. Hence, its CIN has been permanently made 0. The 4-bit parallel adder is a very common logic circuit. Did you know one of the first known examples of a shift register was the Colossus, a code-breaking machine of the 1940s? Now we will learn about sequential logic circuits. Sequential logic, or SL, in digital circuit theory is the set of rules and implementation of circuits that rely on the current and past events of logic states and transitions to determine present logic states. Knowing about combinational logic, CL, the set of rules and implementation of circuits that rely on the actual logic levels, reveals the key points in sequential logic. Logic levels for binary computing usually refer to high or low. In positive logic, 1 is high and 0 is low. Logic circuits are made up of gates that may have 1 or more inputs and usually only 1 output. A simple CL gate is known as the buffer and the inverter, or NOT gate. The buffer output is always the same as the input, but the inverter output is always not the input. Other gates used in CL include the AND gate, the NAND gate, and NOR gate. The AND gate outputs a 1 only if both inputs are 1. The NAND or NAND gate and NOR gate are respectively an AND gate and an OR gate, each with an inverter at the output. Flip-flops. In the case of a latch with control input, when the control is enabled, the latch is in transparent mode. That is, its output changes its state according to the set and reset states. Synchronous flip-flops. In synchronous circuits, the input are pulses or levels and pulses, with certain restrictions on pulse width and circuit propagation delay. Therefore, synchronous circuits can be divided into clocked sequential circuits and uncloaked or pulsed sequential circuits.
In this video, we will learn about the sequential circuits, and we will see how they differ from the combinational circuits. The logic networks which we studied, called multiplexers, demultiplexers, adders, half adders, subtractors, half subtractors, encoders and decoders, these are all the examples for combinational circuits. These are called the combinational circuits. In case of combinational circuits, the output at any given time are dependent on the inputs at that time. In contrast to this, we have got something called sequential circuits. In case of sequential circuits, the output not only depends on the input at that time, but it also depends on the past history of the input. Here I said the past history. So the past inputs have to be stored somewhere. So we need a memory in case of sequential circuits. As we do not have to store any past data with respect to combinational circuits, there is no need of memory with respect to combinational circuits. In case of sequential circuits, there are two basic classifications. One is synchronous sequential circuits and the other one is asynchronous sequential circuits. In case of synchronous sequential circuits, the output changes its state as soon as the clock given. Even though there is a change in the input, and if there is no clock given, then the output doesn't change. So a clock is must in case of synchronous sequential circuits. In case of asynchronous sequential circuits, the output changes its state as soon as there is a change in the input. So there is no need of clock in case of asynchronous sequential circuits. The best examples for synchronous sequential circuits are flip-flops, and the examples for asynchronous sequential circuits are latches. Both flip-flops and latches are used to store either 0 or 1. So these are the memory units. They are used in sequential circuits.
Let's now learn about finite state machines. A finite state machine, or FSM, or finite state automation, plural automata, or simply a state machine, is a mathematical abstraction sometimes used to design digital logic or computer programs. It is a behavioral model composed of a finite number of states, transitions between those states, and actions, similar to a flow graph in which one can inspect the way logic runs when certain conditions are met. It has finite internal memory, an input feature that reads symbols in a sequence, one at a time without going backward, and an output feature which may be in the form of a user interface once the model is implemented. State transition graphs. A state transition graph, or STG, is a directed graph representing the dynamical behavior of a regulatory graph. Nodes of this graph represent possible states of the model, assigning a value to each component. Arcs of the STG represent transitions from one state to another, for example, a change of value for one or several components. Processor operations mostly involve processing data. This data can be stored in memory and accessed from there. However, reading data from and storing data into memory slows down the processor, as it involves complicated processes of sending the data request across the control bus and into the memory storage unit, and getting the data through the same channel. Processor registers. There are 10 32-bit and 6 16-bit processor registers in IA32 architecture. The registers are grouped into 3 categories: general registers, control registers, segment registers. The general registers are further divided into data registers, pointer registers, index registers, and data registers. Data registers. Some of these data registers have specific use in arithmetic operations. AX is the primary accumulator. It is used in input-output and most arithmetic instructions. For example, in multiplication operation, one operand is stored in EAX, or AX, or AL register, according to the size of the operand. Control registers. The 32-bit instruction pointer register and 32-bit flags register combined are considered as the control registers. Many instructions involve comparisons and mathematical calculations, and change the status of the flags, and some other conditional instructions test the value of these status flags to take the control flow to other locations. In digital circuit theory, sequential logic is a type of logic circuit whose output depends not only on the present input, but also on the history of the input. This is in contrast to combinational logic, whose output is a function of and only of the present input. In other words, sequential logic has storage, memory, while combinational logic does not. Sequential logic is therefore used to construct some types of computer memory, other types of delay and storage elements, and finite state machines. Most practical computer circuits are a mixture of combinational and sequential logic. There are 2 types of finite state machines that can be built from sequential logic circuits. Moore machine. The output depends only on the internal state. Since the internal state only changes on a clock edge, the output only changes on a clock edge too. Mealy machine. The output depends not only on the internal state, but also on the inputs. Synchronous sequential logic. Nearly all sequential logic today is clocked or synchronous logic. There is a clock signal, and all internal memory, the internal state, changes only on a clock edge. The basic storage element in sequential logic is the flip-flop. The main advantage of synchronous logic is its simplicity. Asynchronous sequential logic. Asynchronous sequential logic expresses memorizing effect by fixing moments of time when digital device changes its state. Counters. Counters are circuits that cycle through a specified number of states. There are 2 types of counters: synchronous or parallel counters, asynchronous or ripple counters. Synchronous counters. The asynchronous counters are simple, but not very fast. If a counter with a larger number of bits is constructed in this manner, then the delays caused by the cascaded clocking scheme may become too long to meet the desired performance requirements. Asynchronous counters. The simplest counter circuits can be built using T flip-flops because the toggle feature is naturally suited for the implementation of the counting operation. Shift registers. The shift register is another type of sequential logic circuit that is used for the storage or transfer of data in the form of binary numbers. This sequential device loads the data present on its inputs and then moves or shifts it to its output once every clock cycle, hence the name shift register. Serial in to serial out, or SISO shift register. This shift register is very similar to the SIPO, except where before the data was read directly in parallel form from the outputs QA to QD. This time the data is allowed to flow straight through the register and out of the other end. Since there is only one input, the data leaves the shift register 1 bit at a time in a serial pattern, hence the name serial in to serial out shift register, or SISO. Parallel in to serial out, or PISO shift register. The parallel in to serial out shift register acts in the opposite way to the serial in to parallel out. The data is loaded into the register in a parallel format in which all the data bits enter their input simultaneously to the parallel input pins PA to PD of the register. The data is then read out sequentially in the normal shift-right mode from the register at Q, representing the data present at PA to PD. This data is outputted one bit at a time on each clock cycle in a serial format. It is important to note that with this system, a clock pulse is not required to parallel load the register, as it's already present, but 4 clock pulses are required to unload the data. Parallel in to parallel out, or PIPO shift register. The final mode of operation is the parallel in to parallel out shift register. This type of register also acts as a temporary storage device or as a time delay device similar to the SISO configuration. The data is presented in a parallel format to the parallel input pins PA to PD, and then transferred together directly to their respective output pins QA to QA by the same clock pulse. Then one clock pulse loads and unloads the register. The PIPO shift register is the simplest of the 4 configurations, as it has only 3 connections: the parallel input PI, which determines what enters the flip-flop, the parallel output, or PO, and the sequency clock signal, or CLK. Similar to the serial in to serial out shift register, this type of register also acts as a temporary storage device or as a time delay device, without the amount of time delay being varied by the frequency of the clock pulses. Also, in this type of register, there are no interconnections between the individual flip-flops, since no serial shifting of the data is required. Universal shift register. Today, there are many high-speed bidirectional universal type shift registers available, such as the TTL 74L S194, 74L S195, or the CMOS 4035 are available as a 4-bit multifunction devices that can be used in either serial to serial left shifting, right shifting, serial to parallel, parallel to serial, and as a parallel to parallel multifunction data register, hence the name universal. These universal shift registers can perform any combination of parallel and serial input to output operations, but require additional inputs to specify desired function and to preload and reset the device. Universal shift registers are very useful digital devices. They can be configured to respond to operations that require some form of temporary memory, delay information such as the SISO or PIPO configuration modes, or transfer data from one point to another in either a serial or parallel format. Universal shift registers are frequently used in arithmetic operations to shift data to the left or right for multiplication or division.
This is a 74HC595 shift register circuit with 8 LEDs, and I've labeled 3 buttons here: data, clock, and latch. So let's begin with how do you actually shift data inside the shift register. So let's say I want to shift in 1. I would hold the data line high and I'll clock it once. Okay, then I'll let go. As you can see, the LED is still off. That is because I still haven't latched it in yet. So latch is basically just showing the data that you previously clocked in. So once I push this, you can see the first LED light up, which is from the high that I just clocked in just now. So let's say I want to have the second data low. I'll just without pressing the data line, I'll just clock in a 0 and I'll latch it in. So you can see now it's a 0. So if I were to continue and proceed to clock in more data, the data will go from left to right this way. So next, to demonstrate the same thing again, I'll clock in a high. I'll hold this data again, which is now high, and I'll press the clock once, and then I'll press latch. You can see now it's high, which I clocked in just now, then low, then high. Okay, after showing the bits shifting in previously, actually in true fact that you can send all 8 data bits in and then proceed to press the latch. That means you can change all of the outputs instantaneously, so to speak, with the latch button. So let's say I want all of these LEDs to be high. I'll just hold on the data, press this clock button 8 times. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then when I press latch, all of the LEDs will light up. Okay, because I'm sending in all ones into the LED. So to clear the LEDs or to clear the outputs is self-explanatory. I will just let go of the data and I'll clock in zeros 8 times. So once I press latch, all of the LEDs will be cleared. So this is a very good solution if you want to save microcontroller pins.
Now in the end, let us summarize what we have learned in this lecture. Encoder is a combinational circuit which is designed to perform the inverse operation of the decoder. One of the most common uses of combinational logic is in multiplexer and demultiplexer type circuits. Combinational logic circuits are made up from basic logic, NAND, NOR, or NOT gates that are combined or connected together to produce more complicated switching circuits. Combinational logic circuits are electronic circuits that produce outputs based on the states of the inputs. A multiplexer, sometimes referred to as a multiplexer or simply a mux, is an electronic device that selects from several input signals and transmits one or more output signals.